Preview. We're excited you could join us today for David Klee's session, Virtual CPUs Right to Ludicrous Speed. This 24 hours of PASS event consists of 24 executive live webinars delivered by expert speakers from the PASS community. The sessions will be recorded and posted online after the event. To access any on-demand sessions, please visit the pass.org site using the 24 hours tab. And my name is Robert Miller, and I have a few introductory slides before I hand the reins over to David. If you require technical assistance, please type your question into the question pane located on the right-hand side of your screen, and someone will assist you. This question pane is also where you may ask any questions throughout the presentation. Feel free to enter your questions at any time, and once we get to the Q&A portion of the session, I'll read your questions aloud to the speaker. You are able to zoom in on the presentation content by using the Zoom button located on the top of the presentation window. Please note that there will be a short evaluation at the end of the session. Your feedback is important to us, so please take a moment to complete it. It will appear in your web browser. Next. I'd like to take a moment to thank our presentation sponsors, Quest, Melissa, and Nutanix. The staging at 24 Hours of PASS would not be possible without their generous support, and they are the reason this event is available free of charge. Make sure you explore everything else PASS has to offer for data professionals. You can join local user groups around the world, special interest groups, find free online resources through our Learning Center, and read up on the latest community news in the Connector newsletter. Next, I'd like to bring your attention to the upcoming PASS Summit, taking place in Seattle, Washington from October 31st to November 3rd. PASS Summit 2017 features over 200 sessions with world-class data experts. It's the perfect place to connect, share, and learn from industry experts around the world. To find out more, please visit www.passsummit.com. And without further ado, here is David with Virtual CPUs Right to Ludicrous Speed.
Thank you. First of all, I just want to say thank you all for taking time out of your day, evening, morning, wherever you're at. I really appreciate you signing on to listen in. This is just a taste of what you're going to get if you're able to make it to the pre-con at the PASS Summit, where it's all about virtual SQL servers and maximum performance. My name is David Klee. I'm lucky enough to be a Microsoft Data Platform MVP and a VMware vExpert. I started my own company about 4 years ago to really focus on how data and infrastructure come together. And we have a lot of fun sharing a lot of the knowledge, because you should have the maximum possible performance out of any virtualized infrastructure. You shouldn't have to blame the environment. You shouldn't have to blame any of the folks managing it. It should just work. So bottom line, this goes into that. DBAs have some very interesting knowledge gaps. Most of us come from development backgrounds. So first of all, what I want to talk through in kind of the agenda for the evening here, what is virtualization? What is hardware? How do they work together? How do they contradict? And then we're going to really do a deep dive on modern CPU architecture and everything that you need to know in order to tune your SQL Server to maximize the performance. Specifically, CPUs, cores, and sockets, what is NUMA and memory locality. And then what we're going to do, we're going to do a deep dive, a little step up in the infrastructure stack, and we're going to talk about the hypervisor and how it handles resource scheduling. So the queues, the resources, any potential overcommit, queue balancing, there's right sizing involved, and then how do we deal with SQL Server and make it line up with the rest of the environment. So virtualization basics. Fundamentally, you've all heard me say this before, all virtualization is an added layer between the hardware and the operating system that allows you to kind of compartmentalize a operating system, whatever runs inside it, and give it access to the resources in that physical machine, namely CPU, memory, network, and storage. And then what it does is, in order for it to be able to share these resources between multiple virtual machines, which can all run independently of each other and they don't even know the others are there, it provides resource queues for these VMs to get access to go do what they need to do on the physical resource. Interesting thing, every single thing that you do inside that virtual machine is placed into a queue. The operating system, the little, Windows, Linux, whatever it is, it doesn't know it's in a VM. It thinks it's got that hardware right there. Every single thing it does, though, goes into a queue at the hypervisor. The time spent in the queue is completely variable, and it really matters based on what's going on in the physical machine. Could it be end of the month and there's just tons of activity with reporting, with data warehouse work, tons of activity with people putting in last minute orders. It changes. It doesn't really stay static, and we have to accommodate for that. The other challenge is these queues are not necessarily first in, first out. Things can be prioritized, things can cut in line, things can be deprioritized. Where does this fall for you? We don't know. The challenge there is if there's imbalances, if there's a lot of overcommit going on, or if the environment is struggling to accommodate the resources underneath, the whole thing can slow down. First and foremost, it hits the CPUs, which is one of the biggest silent performance killers you've got in a virtual environment. It's really the origin of why virtualizing SQL Server to begin with got such a bad rap. It's not that way anymore. In that infrastructure stack, inside the physical machine, I call it the four main food groups, and I took that from a friend of mine, Michael Corey. The number one concern for us at this point in time with virtualization where it's at is going to be CPU. These are the things that we're really concerned with. Memory, luckily, most of the time, not all, but most, when it comes to memory for SQL Server in a virtual environment, we're not oversubscribed, meaning we've not allocated more than we actually physically have available on that physical machine. So in those situations, it's less important. Now, it may not be this in your environment, but it should not be oversubscribed, at least not around. Storage, arguably, if we've got the budget, we've got really fast storage underneath all of this because latency when it comes to SQL Server really matters. So if we can get the storage fast enough, the interconnects shift, or the bottlenecks shift further north in the infrastructure stack. It could be onto the interconnects between the flash array and the physical machine. It could actually be on the way the physical machine is configured. It could actually be that it's good enough that it shoves the problem back into CPUs and the way the database is designed and managed and orchestrated. So it may be okay. Networking, normally networking is not really a problem. Occasionally it is. We see async network I/O, and so, a lot of times that's the app. But every once in a while it's network. But it's not that common. So we got to focus on CPU. So when I say resource queues, there's a physical machine. There's our four main food groups: CPU, memory, storage, and network. Every single thing has got a queue: CPU, memory, disk, network. And when the VMs go to access this, these things can start to stack up. So we're going to tackle CPU here. So first of all, what's a CPU? Well, a long time ago, it used to be a processor that had a core and it would do what you wanted. Well, it's not that necessarily the same today. We've got really complicated CPU architectures. So in today's CPU architecture, we have what we call a CPU package, which is a socket chip that has numerous processing cores in it. Each one of these cores has dedicated level 1 and level 2 cache. And if I make an analogy, it's kind of like saying we've got a phone book, which is everybody in a town, that archaic thing called a phone book, and then you've got your personal contact list, say in Outlook or whatever, and that's kind of like level 2 cache. These are the people that I call frequently. These are people that I know. Level 1 would be all the people you have programmed in your phone. These are the people that I call all the time. Cache is exactly the same. You have last level cache on there, which is shared between the cores. And you got a whole bunch of stuff that's not necessarily related to the core itself, but you've got other stuff that kind of coordinate activity between them and deal with memory access and all of that. I kind of group it into this bundle called an uncore. That's what it looks like. Looks pretty cool. Newer architectures are a little bigger. They've got all these little pins on the bottom, but that's it. That's the brain behind this entire thing. It's pretty fascinating. So that chip goes in this thing. This is called a motherboard or main board. Now this particular motherboard, we have spots in here for 4 CPUs. Most of what we work with today has two. Most of the time you're not dealing with one. There are some servers out there that can go up to 16 sockets. These are massive, complicated, very expensive machines that are incredibly designed, and I would give anything to be able to play Frogger on one, because you need 24 terabytes of RAM and 768 cores to play Frogger, right? Well, functionally, if we step back, why do we have those individual setups like that? So back in the day, let's go back about 2003, 2004, if I wanted a really, really monstrously large server, I would go buy one and have a handful of CPUs, I'd have a lot of RAM. Well, back in the day, this was called an UMA, Uniform Memory Access Architecture. And what happened here was that the CPUs were connected to this thing called the North Bridge, which contained a memory controller, and that was connected to all of your memory. Anything handling I/O, anything other peripheral devices, it all had to go through this North Bridge in order to get there. Over time, memory densities went up, CPU densities went up, and what we found was that this component was functionally a bottleneck to performance. They just couldn't keep up. So about 2003-ish, AMD pioneered it on x86, and Intel really came along and perfected it. They came up with this thing called non-uniform memory access. So that is what's called a NUMA node, and it is a CPU socket, and all of this memory right next to it, physically located as close to the chip as you can possibly get. And then what we have is groups of memory and CPU scattered around the motherboard. This is basically the way this architecture works. Instead of having that memory controller globally centered on the motherboard, they actually embedded one into the CPU package. So now every single CPU package has this memory controller, and it can directly get to the memory that's connected to it. Now, you can have 2-socket, you can have 4-socket, you can see they've got pathways, so these things can communicate as fast as possible with each other. Well, it's still not perfect. We still have this thing called physics to worry about here. And functionally, we don't have independent pieces here. You know, if we can take our workload and we can say, hey, program, you're going to run on this NUMA node. That memory lookup is really, really low. We're talking roughly 7 to 8 to maybe 10 nanoseconds. That's an incredible feat of engineering. It's amazing. Now, that CPU socket can still reach out and grab memory from another CPU socket, but it's aware that it's distant. And the interesting thing here is that because of physics, it's about a 3.1 times performance hit if you go remote than local. That's a big deal, especially because of the way SQL Server uses memory. SQL Server makes this assumption that memory is faster than storage, and to this point in time, they're 100% correct. So it keeps all working set data in RAM. If we can accommodate and tell SQL Server through all of these different layers what this configuration is and how the VM lines up with it, then we can take our workloads and we can pin them. So that way, if the SQL Server thinks that it's a local memory block, but in actuality it's a remote memory block, we can make things faster. And I'm talking 20, 30, 40% faster just by tuning this individual layer. So bottom line, why does this matter? You know, we're not hardware geeks. Well, I kind of am. But functionally, SQL Server is NUMA aware. So is Windows. So is Linux. And what we need to do is we need to balance this out. Misalignment is one of the most silent performance penalties you will ever see. I was on site a couple months ago at a place. We measured a 41% performance hit on their production SQL servers because of misalignment and oversubscription. It was just from misalignment. The hypervisor can really blur the lines on what is physical NUMA in terms of how it presents itself to the virtual environment. If we do this wrong, it creates an immediate out of balance situation. Silent performance killer doesn't get any bigger than this. The good part is it's preventable. It's also detectable, but your VM admins probably aren't watching for this. They don't know this layer. They don't know how SQL Server manages this, and most of the time they just treat it like a file server. So we got to work with them. We all know SQL Server performance is an incredibly close second to availability in terms of what our job responsibilities entail. SQL Server is extremely latency sensitive with all of these layers. This is the fun part. So now, when I'm a VM admin, so I wear a lot of roles in here. If I'm a VM admin, this is what I see. I want to look to see what's going on this physical machine. So I click and I see that physical machine. I go, oh, I'm barely doing anything with CPU. RAM memory's about a third full. No problem. Okay, well, hey, DBA, you need a new VM. Let's go create one. Well, you need 16 sockets. You notice here, this is the virtual machine settings. Cores per socket and sockets. The only time they ever see that is if they expand out the advanced properties for CPU. Most of the time they just pick 16. And that just says, I need 16 sockets, each with one core. Now sometimes a hypervisor will kind of guess at the virtual NUMA topology. Sometimes it doesn't, and it gets it wrong. Or sometimes VM admins think they know better based on, because forum posts and things like that, because that's all true, right? Not really. So they'll go set it to whatever, and they don't bother to test this. And we don't know any better because we think virtualization is supposed to get it right. It's not the virtualization layer's fault, it's the admin's. What you can see to go spot check this, one, just open up Task Manager. Down at the bottom there, sockets, virtual processors. You got 2 sockets, you have 16 total processors, so you've got 8 per. Open SQL Server. Hit the right click on the instance, hit properties, go to CPU, and look at that. NUMA node 0, NUMA node 1. You can see exactly what cores within Windows make up those individual NUMA nodes. Now, the bottom line here is, first of all, how many CPUs do we actually need? And I stress this. We have to go through a right sizing analysis. The reason, if you look at this image right here, this was live, from a customer of mine. They were throwing CPUs at it and just, it's slow, it's not getting any faster, we're throwing more CPUs at it. And well, look, you got 2 that were really busy and everything else was idle. You can throw all the CPUs at it you want, it's still going to just use the 2 for whatever reason. That workload was just pinned to 2. Didn't matter. Bottom line, what are we using? What are we actively using? You have to figure out, based on perfmon data, you got to figure out from whatever metrics you've got. And it's not just a one-time thing. You got to size it for right now. Anything that's just not actively being used inside that VM is going to act like a parachute attached to the back of a car. We got to size it for now. We got to give a little bit of headroom for now. But we size it for now, not what you think this thing is going to use 2 or 3 years from now, or not what a vendor tells you need. My goal, right sizing during normal routine business operations, and I may exclude maintenance operations from this, use your best judgment there. I'd like to see the target CPU utilization between 40 and 60%. This might mean this VM is going to be a little bit smaller than you think it should have, but do testing, do your due diligence, verify that I need that amount of CPU in order to get the proper performance. Anything more than that is going to be wasted. You potentially waste SQL Server licensing. You definitely waste scheduling those resources on the physical machine. It just slows it down. And then as things grow, databases get added, apps change, users get added, data certainly gets added. Resize the VM is necessary. It's about 5 clicks for a VM admin to change this, and it takes about 2 minutes of downtime during some maintenance window down the road. So we got to create a baseline. Third-party utilities, there are a lot of really good ones out there. I don't want to name any names because I don't want to seem like I favor any of them. And a lot of them work very well. If you don't have the budget for any of those things, Windows Perfmon works great. There's a free PDF out at my site, not going to market anything, I don't ask for any contact info. It shows you how I like to go set up Windows Perfmon. It works really well. It's there, it's been there forever. Now, everybody out there tells you to go collect Perfmon. What do you do with it? Well, this is so new, I don't even have a proper web page for it, but I'm going to be open sourcing a PowerShell script really soon out on GitHub, so stay tuned. This is going to be free PowerShell to extract the data from a PowerShell file and shoot it into a SQL Server database so we can go mine it. We can go do the stuff that we're most familiar with. Right now there's a rough PowerShell script out there. Go check it out if you want. Again, don't ask for any contact info or anything. Have at it. I want to make this a community project. I want to see this thing grow, because if we don't have the budget for a proper utility, we need to go build our own. and I'm tired of watching people waste hours and hours and hours building their own. Perfmon counters, this is what you can do with some of this data. I mean, it's awesome. This is a actual customer environment of mine by CPU core, sampled every 30 seconds, averaged into a median, so not an average, but a 50th percentile every roughly 5 to 15 minutes during a normal day. This is a week that was been rolled up. And you can see they do maintenance right at midnight. They've got a blip of activity right at 5 a.m. and then about 7:30 in the morning people start to come into work, and we've got a normal bell curve throughout the day. Looks like some people leave early and some people work a little bit late, and then we've got some work that happens at 9 and at 10, early 8, 9, 10, 11, 12 at night. If I want to right size this thing had 8 CPUs in it. You notice the only time we ever really get a spike on here is at 8 o'clock p.m. Functionally speaking, but that's only one core. So if I were to consolidate the cores on here, I'm going to see the consumption in the afternoon go up, but where's that 40 to 60% range? So they've got 8 CPUs. If you look, I would probably start my testing at 4 CPUs. Sounds crazy. Now again, start the testing there, but functionally speaking, it could actually perform slightly better if there's not a lot of CPU contention in the background. And if there's a whole lot of CPU contention in the background, this could actually gain 10-15% by cutting the core count in half. I know, it sounds crazy, it sounds contradictory to everything we've ever known as a DBA. But virtualization, there's so many things that are similar, but this one's different, and this stuff matters. Placement now. This is where we really have to start understanding the NUMA side of things. So let's say I've done my right sizing analysis and I know how many CPUs I need. So take your physical machine, and to understand what you've got here, you can either ask your infrastructure team, and they'll give you the specifics. They shouldn't hide that. If they do, get a copy of CPU-Z, download it, run it inside the VM. It'll tell you the make and model of the CPU architecture. And then just hit your favorite search engine, look for that. It'll tell you exactly how many sockets are in that physical machine and how many cores. Now you may need to go to your infrastructure team to get the memory assigned to each one of those sockets, because the CPU-Z won't tell you that inside a VM. But you'll get a basic understanding. So this example, 2-socket, 12-core virtual machine, 128 gigs of memory per socket, so 256 gig total on the physical machine. So now I've done a right sizing analysis, and I know I need a 10-core VM, 64 gigs of RAM to facilitate all the I/O buffering that I need. Well, 10 fits inside 12 very comfortably. So configure the VM for a 1-socket by 10 virtual core. Interesting thing to note, on most modern hypervisors, if you have 8 or less virtual CPUs, it doesn't matter what you set that core versus socket count, it won't extend it. Now, sometimes that threshold is pushed upwards if you have really high core counts per socket. Just kind of depends there. If you have proven that you need that split, you can force it in. Hit my home blog. There's a bunch of posts on there for that. Now, what if I need a VM that's bigger? What if I need 16 CPUs? 16 doesn't fit comfortably inside of 12. So start your testing, and I stress test, with a 2 virtual socket by 8 virtual core VM. And if I have 128 gigs of RAM, well, there's 128 and 128, and it looks like it'll fit inside, but there's a little bit of overhead to manage memory, and a little bit of memory there for the hypervisor itself. So you'd actually have maybe 125 gigs available in that socket. So if you do this 2 by 8, it'll cut the memory footprint in half per NUMA node, and you end up with basically an 8-core VM with 64 gigs of RAM running on each one, just pieces of the whole. So split it. Straightforward. Start your testing there. This may not be where you end up. If you want to go confirm the CPU information inside the VM, go download MS Core Info from sysinternals. It's available at that link there. Run it from a command prompt. Check it out. You have a logical to physical processor map. It's pretty cool. It shows you which processors line up to which NUMA node. Really cool. This is the neatest thing right here. You want to go see that performance hit between the NUMA nodes? It tells you. Cross NUMA node access cost relative to the fastest. So in this case, NUMA node 1 accessing itself is the fastest. NUMA node 0 accessing itself, we've got an imbalance with the memory under the hood of this thing, and it may not be properly balanced under the hood. There just may be a lot going on, and you can see it. The time Windows comes on, that's actually the performance hit that you take if you have a cross NUMA memory lookup. That's a substantial hit right there, especially for CPU access and memory. It's free utility. Go check it out. It's pretty cool. Now, with the hypervisor, this is your average VM host. You've got shared storage. In this case, we've got two 2x12 hosts. In this case, I've got just 6 virtual machines between 3 hosts. Well, it's not like we've got one thing going on total. You've got VMs that are just going berserk. You've got these things doing all kinds of stuff. And as a result, things are going to slow down, potentially. That's just a 2-to-1 overcommit. We found one the other day that was a 12-to-1 overcommit. I will say things were not running very well there, but we're working with them to clean it up. So what do we do? Here's your scheduling queue. This is what actually is going on. You've got VMs that are submitting tasks constantly to their individual queues. Now this is I'm ready to run this task, but the physical machine isn't quite ready yet. So get in line, no problem. This is the execution task. So one of these things, tiny footprint, can usually squeeze through pretty well. But if I've got a really big VM and it's trying to push a lot of this stuff through, so right there, you can see drags on. Bigger VM, if there's a lot going on, it slows down. Now, the hypervisor is awesome. And, I'm a nerd, I know. It tells you how long these things spend in the queue. You just got to know where to look for it. And I'll flat out say, most of the time your infrastructure teams do not know this stuff. They've never had to worry about this stuff before. They're probably not watching it because the physical machine CPU consumption can look like it's very low, but if there's a lot of imbalances going on, these delays can just really drag on. So the first one here, if you have something with perfmon or WMI collectors, anything that can go collect it out of the Hyper-V host, per VM, there is a measurement called wait time per dispatch, and it does it total, and it does it by virtual CPU. This is measured in nanoseconds. What you want is either the average value across all the cores or get the individual core values if you want to see if there's an imbalance in there. Set the collection for 1 second duration, and then get the average for that collection duration over, say, 30 seconds. And I like that 30 because anything less than that, can't really do much about. Anything greater than that, you may miss a spike. Take that, divide it by the total sample interval nanoseconds, multiply it times 100%, and what you end up with is an average performance loss. And this is a collector from one of our customers. In this case, the counter value looks really bad, 25,000, 22,000. Realistically, it's like 0.25% or lower. No big deal. Things were really good there. But that it's as simple as that. That's the gross performance hit on that VM at that point in time. Now, I would say that on average, SQL Server looks, with the way parallelization works, some things are parallelized, some things are not. I would claim that the average performance hit to your SQL Server is roughly double what that percentage is. So most of the time, it'll be 0.5%, 1%. So that translates to 1 or 2% within SQL Server. Functionally speaking, I can barely even measure that, let alone actually have that impact a production grade workload. And in that case, it's fine. But then there are other cases where it could be 10, 15, 20%. Well, double that. That's notable. Definitely noticeable. That's when people start calling. You don't want that. You don't need that. It's bad for the business, bad for you, bad for the end users, bad for your customers. Get in front of it here. If you're running VMware, very similar counter. It's called CPU ready time. This one is measured in milliseconds. And same thing, we get the sum of all the machines, or we get the individual core values. It looks like it here. Instead of being a variable sample interval like you get with Hyper-V, it's whatever you collect it at. Here, it's a fixed 20-second interval for the real-time view. Take the sum total of everything, divide it by the number of cores, divide it by 20,000 milliseconds or 20 seconds in that polling interval. make it a percent. Once again, average performance loss. In this case, that chart there looks really bad. Functionally speaking, that's about as good as it gets. That you're looking at less than 0.1% performance hit. It's awesome. Now, here's another challenge. The bigger the VM, we have individual queues for each one of the virtual CPUs. What if something cuts in line in front of, let's say, one or two of them, but not all of them? You end up with an imbalanced state. And again, all of this is going on underneath the virtual machine. You can't see it. Well, what if, let's say, things are just speeding along and the queue is just slow for a bunch of these things? And in this example, one's way ahead of the other. Well, the hypervisor detects this, and it goes, hey, this one's going really, really fast. It's hurting the synchronization at the operating system. There could be things that are taking a hit there. So it'll actually suspend one of the virtual CPU schedulers to let the others catch up. And once they've caught up, then it goes, okay, you're good to go. This is new. This is a newer construct in the hypervisor world because we've got virtual machines now that can do VMs a whole lot bigger than they ever used to be. You know, originally it was 1 or 2 CPUs and that was about it. And now you can do 240 CPUs in a VM. That's incredible. The bigger the VM, the more you have to worry about this. Now, unfortunately, I have not found any means to go get this out of Hyper-V. And if there's anybody out there that knows the equivalent of VMware's co-stop time, let me know. I'd be happy to put that up on the blog post and give you a great big thank you for it. But functionally speaking, the only one I know here is co-stop. And this is one that VM admins do not know about. It's not even persisted in the vCenter database, which is really bad. It's only available in the real-time view. So if there are major problems here, they don't know about it. They don't have the ability to go back and look at this stuff. And if these things become problems, what you'll get is the VM will just go unresponsive for 1, 2, 5, 10 seconds at a time while these things rebalance under the hood. You know, it's measured in milliseconds, just like ready time. It's, you know, calculated very similarly, but I don't even look at it as a percentage in this case. If I see big spikes of rebalancing, that's a problem. The image on the screen here, no big deal. For a big VM, that's perfectly normal. They're little tiny things here and there, nobody will ever notice. But if you get sustained duration, you know, a minute or two, or if you see the spike be really, really big, we're talking thousands of milliseconds, that's a major problem. And this is one of those things you got to get in front of. Now, this is why, you know, hypervisor aside, you got to get access to the hypervisor. You have to be able to go see this stuff. So if it's Hyper-V, get access to System Center. You know, SCOM is your friend, and you know, with everything going on. If it's VMware, please go get access to vCenter. You don't need to be able to change anything, but read-only access is what you need in order to be able to see this stuff. And I implore you, this is critical to maintaining performance, and they're not watching this stuff closely, but you need to. Now, with SQL Server, we've come full circle. We've got the physical machine boundaries that we know we need to align with. We've got the VM that we know how to align it now. We get to SQL Server. Those two values right there, cost threshold for parallelism, max degree of parallelism. If you've never played with these things before, the defaults are probably not good on modern machines. The default of cost threshold for parallelism is 5. What that originally was a particular query took 5 seconds on this one guy's computer at Microsoft. Those days are long gone. Now it's basically just a number where if the calculated value of complexity for a given query exceeds that metric, SQL Server will attempt to parallelize it. And the max degree of parallelism is if it's going to parallelize it, this is how many CPUs it's going to go up to. The default of cost threshold is 5. I would claim instead of just going and throwing a blanket 25 or 50 out there, start at 50 and do some testing. Jonathan Caius has got a really good post out there about how to go scrape the execution plan and get these values. Throw them in Excel, put them in a scatter plot, go see where they line up, do some testing. Option max stop X will let you take individual queries and force certain amounts of CPU to be applied to each one. Figure out your sweet spot. We've got one. The sweet spot on it is 13. We have another one. Sweet spot is, I'm not kidding, 81. Just random numbers like that, and that's the sweet spot for those apps. Go do that. Test, test, test. Don't just blindly pick numbers out there. The other one here, max degree of parallelism. If you're going to virtualize and parallelize, my starting point for this number, and it may not be the end point, is the number of virtual cores in one virtual NUMA node. So if I have a 2x8 VM, I would start my testing with max stop at 8. Now again, if your application prohibits this, like SharePoint or BizTalk or anything else, then set it to what the vendor requires. But otherwise, start your testing at 8, because if we can tell SQL Server to pin that workload to one NUMA node inside the VM, life gets better. And what you get is balanced harmony. You've got SQL Server with one huge query, and it goes, hey, keep that workload here, keep the memory fast. SQL Server tells Windows to do this properly. Windows or Linux tells it to stay at the hypervisor and balanced. The hypervisor then pushes it through the physical machine boundaries just fine, and you've got alignment. When you do this, when all of these CPUs are being actively used, the amount of scheduling delay drops, your machine runs faster, everybody else on that same physical machine, they don't feel the impact with all of this, so they speed up. And if you do this in mass, I claim that you can actually increase the VM density, which cuts down on licensing, and make things faster. If you do this right, it works. Work with your infrastructure team. It does matter. In order to do this sounds scary. When applicable, and I claim you need all the evidence and the proof in the world, this is why that perfmon thing is out there, reduce your virtual machine allocation, especially with CPUs, most of the time with RAM as well, when applicable, when necessary, do the math, do the work to actually prove that this is what you need, and then test to confirm, and that way everybody's on board with it. Align it with the vNUMA boundaries. Work with your VM admins to get those VMs configured properly, and don't be afraid to throw a 2 vCPU VM out there, or 4. Small VMs can do a lot of stuff if they're tuned properly and the workload does well. You don't need a 32-core VM if my phone can run your database. It reduces the CPU scheduling. Get access to the hypervisor so you can actually go observe this. The smaller VM footprint makes it easier to schedule, less delays, blah, blah, blah. It works. Reduce the VM workload. If you've done this and you still have exceptionally high delays, reduce the workload. Load balance the VM cluster. A lot of times they may not have load balancing turned on. They can load balance this. If there's a hotspot on one machine that's causing a problem, they can shuffle VMs around. A lot of times they can do this hot and live. It doesn't impact anything. Remove, if you've got really crazy VM workloads, remove them from your host. Get them onto another one. Shift that problem. You can use resource pools to say, I have business critical production SQL servers that should always get top priority to those physical resources. The way I like to do it, I have tier 1, tier 2, tier 3. Tier 1 is business critical production. Tier 2, it could be, stage UAT. It could be business not so critical production. Utility database servers, things like that. And then tier 3, I usually do pre-production. Now, feel free to set those boundaries on your own. I usually like to do 3 because there's, easier ways to make those work instead of having to juggle shares and that kind of stuff. Do those, and do those. Okay, that was a lot of info that we just flew through. This is just a piece of what we're going to get when it comes time to actually aligning the entire VM and making sure that the VM farm is set up right. Any questions with the virtual CPU side of VM tuning?
David, there is one question. If you have a 2x8 host that is also a hyper-threading, so you're a total of 32, is there a good reason or vice versa issue for giving more than 16 total vCPU to a VM?
It's a really good question. I generally don't like to allocate anything more than the physical machine resources on the host. And that's because a hyper-threaded core is not as powerful as a full physical core. It's essentially, think 100% total minus what you're using with the physical core. That's what's left over for the hyper-threaded core. So if those CPUs are really, really busy on the physical cores, you don't have much left. I generally like to say a hyper-threaded core is roughly 0.2, maybe 20% of what a regular core is kind of how I do my math. Most when it comes to vCPU calculations, I just completely ignore hyper-threading. What we get with that then is that the VM really should not exceed the physical CPU boundaries. Now, if you find that your workload works better like that, there are commands that you can tell it to better align and actually start to leverage the hyper-threaded cores. But again, it's really rare for me to ever need to do that. I think I've only had to do it 2 or 3 times in the last couple of years, and that's because of just really squirrely workloads.
Now, is an extension, and I'll just go ahead and ask that extension, is it better than just to turn off hyper-threading?
Another good question. I would claim no. The hypervisor does a really good job of affinitizing to physical cores. If there is extra, basically if there's headroom left because of the hyperthreading cores, and the physical machines not being entirely consumed, the hypervisor will actually leverage those cores to do balancing of lower priority things or even its own internal management mechanism. So don't disable the cores, just don't plan on using them for virtual CPU activity. It'll do a really good job of balancing that itself.
Okay. Next question. Could the vCPU queuing result in higher CX packet weights as not every scheduler runs at the same speed on older versions of VMware?
Yes, and not just VMware, Hyper-V and OpenStack and all the other variants out there. It can. Arguably, it's hard to correlate the two, but it most certainly can happen, especially if those virtual CPU queues are very much out of balance with each other. SQL Server will actually see that, and it'll queue up CX packet and maybe a little bit of SOS. This is where, an individual counter, to quote Paul Randall, it's kind of a knee-jerk reaction to want to react to one of those. This is where more digging needs to go into it to say, we have elevated CX packet. Okay, well, let's look at the hypervisor layer and see what we've got. Let's look to see SQL Server CPU consumption versus Windows and really try to put more of those pieces together. And with that, you get a better picture of how these things play nice or don't.
Okay. And those are the 2 questions we have received so far.
Okay. Anybody else have any questions? Doesn't have to be about CPUs.
I'm sorry, go ahead.
Go ahead.
I was going to say there was one question that was asked early on, but you sort of answered it during your presentation. I'll go ahead and ask it again in case you want to expand on it at all. Mm-hmm. The person asked that he heard recently that they forgot from where that crossing NUMA nodes is no big deal anymore, and he was looking for your comment.
Crossing NUMA nodes is less of a big deal than it used to be. And by big deal, I mean terribly awful. It's better than it used to be. It's still not one-to-one. It's still not equal in terms of memory and scheduling. You may have heard, it may have actually been something called cluster on die, where some of these big, 18, 24 core count CPUs, they'll actually have multiple packages on one package, where a 24-core physical CPU may actually be 2 12-core independent packages on one CPU die. Crossing those boundaries internal to one socket are a whole lot less impactful than if you cross physical sockets on the motherboard, but there's still a hit. There's a really good book out there if you're interested in reading this. I just got done with it actually. It's called vSphere 6.5, a host resource deep dive. And forget the fact that it says VMware on the book. 99% of the book is dealing with advanced CPU and memory scheduling and architectures internal to those chips. It has nothing to do with the hypervisor itself. Phenomenal read. Definitely go pick that up.
Okay. We had a question come in. The question is, we have a testing environment where a workload lasts 40 minutes at most. Can we still tune to improve performance?
Absolutely. Yeah, I mean, every one of these best practices, dev, prod, you name it, it all helps. So you can, of course, tune the SQL Server side just like you would in prod, but, from a VM perspective, in my opinion, there should be no differences in the VM construction between prod and dev. The only thing that the VM admins may do is want to give you less CPUs and RAM, because arguably dev can take a performance hit where production can't, but all the best practices still apply.
True. Okay, cool. Those are the questions that have come in so far. We still have a couple of minutes.
I think I talked fast.
It was a very good presentation.
Oh,
I always like listening to your presentation because I always learn something new.
Thank you. This stuff is fun. I'm a hardware nerd. I'm getting 4 more quad socket machines for my lab this coming week. Yeah, yeah. The power company really likes me right now. But Azure Stack is about to be released, so I'm going to play with that too.
Cool. So, a question came in: is there a list of resources somewhere? I imagine this is on your personal blog.
Yeah, it's a little out of date right now, to be honest. I used to have a book section up there. What I do need to do is I need to update that. So I'm going to take that as a to-do for this weekend when I get back home and settled. So yeah, check my home blog, just davidklee.net, out this weekend. I'll have a resources page with a bunch of book recommendations and potentially some different blogs and threads out there with a lot of really good info on SQL Server virtualization. And here's the fun part. This isn't just limited to on-prem virtualization. Every single thing that I talk about directly applies to the cloud. You may not have access to some of these layers, but the mindset and the methodology of doing this directly applies out there. So, virtualization is the first step to cloud. If we get in the habit of doing this now, we make things faster out there and we save ourselves money.
Speaking of cloud, can you do anything to monitor an AWS SQL Server?
Oh, yeah. Yeah, I mean, CloudWatch works really well. If it's AWS, you have EC2 instances, you've got RDS instances. RDS, you get CloudWatch where you can monitor some of those perfmon stats remotely. If it's an EC2 VM, then anything that you would normally do goes. It's just a VM out there. Same thing with Azure.
Another person asked, where will we be able to download the PowerShell you mentioned earlier to capture perfmon data?
The link is on the slide. Keep checking back. That page is going to be updated here really soon. I'm trying to figure out how to normalize the content out there. It's just a hfxte.ch/perfmonposh. I'll put that out on my blog here really soon, and it'll be in the deck to download.
Okay. And somebody else just asked, what's your blog URL?
Yep, there's 2. davidklee.net is my personal blog. The company blog, where a lot of these free resources are located at, is just heraflux.com. Again, no marketing pitch. I just put free tools out there because it's fun.
You may want to spell that one.
HERAF as in Frank, LUX.com.
Okay. And we still have a couple of minutes if people want to ask a question. About 3 minutes.
Yeah. Well, I would say, everybody, this is just a piece of what you're going to get with this deep dive. And, it's one of those, after the pre-con wraps up, I love troubleshooting. So if you've got individual specific challenges with your virtual environment, bring a laptop. I'll take it out to the lobby and we'll work until midnight taking a good look at your environment to see what kind of tuning we can do.
2 questions, one of them quick. Have you posted updated pictures of the home lab yet?
No, but we are live, and I figure now is a fun time to do this. That's half of the current lab.
Yes, there's a power company that likes you.
Yes, there is.
So with a mixed load, high amount of transaction batches with OLTP OLAP, would you be more likely to make MaxStop a little less so that more single-threaded queries can run while also allowing more queries to go parallel at the same time?
Yeah. Yeah, that makes perfect sense. Again, it's situational based on your workload. If it's a really highly concurrent environment where there's an opportunity for some critical queries to go parallel, yeah, it makes perfect sense. It's one of those, whatever you would do in the physical world with situations like that directly applies to the VM layer. But that's also why tuning the VM layer to get it to line up, well. That's why it's so important, because if you do that and the layers don't line up, then it's just going to get worse.
Okay. Cool. Yeah, I think anybody that's considering doing any kind of significant SQL on VM type activity or moving to the cloud, coming to your pre-con at PASS, I've done your day pre-con a couple years ago, and that was very enlightening. And so anybody that does that is going to learn a lot.
Awesome. Thank you. It's one of those, if anybody's interested in becoming a serious nerd and running a home lab, and it doesn't have to be anything crazy, but let me know. It could be an old desktop parked in a corner. I talked it up yesterday to a friend of mine here on site, and he ordered a server this morning. I mean, he ordered one, I think it was $680. It's 12 cores, 144 gigs of RAM, and 2 terabytes of hard drive space. Perfect home lab. He's going to put Hyper-V on there, and it's just going to work. It's one of those, throw it in the basement and run away.
Excellent. 2 generations old, those things are still very good.
Oh, yeah. I mean, you don't need the latest and greatest and dropping 20 or 30 grand on a piece of equipment just to get it to turn on, to give you something to pound on. Because let me tell you, there's no better way to learn this stuff than in an environment that you can break and nobody yells at you when you do it.
Yeah. And I think we will, if you move to the next slide, we're going to probably go ahead and work towards ending this. One last person very humorously said that he signed in late and asking if you could repeat everything before you logged in. He's just kidding. It's a great info, and thank you very much.
Awesome. Well, hey, check out the recording. Everybody, I'm on Twitter. Feel free to message me if you have any questions. It may take me a little while to return your tweet, but I will return it. And ask away. And up next, Ken, Azure SQL VM. I'm going to be tuning into this. He's an awesome guy, and it's sure to be great content.
Excellent. Thank you, everybody, for attending, and we do look forward to your attendance. And if you are so desiring, I highly recommend it to join us in the next session.
Awesome. Thanks, everybody, for attending, and hopefully I will see you all at the summit.
Thank you.
Thanks.